Okay, so we're going to talk about inversely proportional relationships. And so up until now, we've talked about proportional relationships, but I guess we should be a little bit more specific and say we've been talking about directly proportional relationships. And the idea is you have two quantities that are in a certain ratio, and if one increases, the other increases. And the big difference we'll see with inversely proportional relationships is that you'll have two quantities where one will increase and the other will actually decrease by the same factor. Okay, so that's why they're called inversely proportional relationships. And one of the most important things is to recognize when a problem is an inversely proportional problem, as opposed to what we've been seeing in directly proportional problems. So they look very similar, but we're going to have to develop some tools to be able to differentiate one from the other. So let's see some examples. All right, so here's an example of a proportional problem. We're making some green paint. This particular type of green paint is made by mixing blue paint and yellow paint in a 3:2 ratio. So we want to know how much yellow paint should I add to 12 gallons of the blue paint to make this particular hue of green that's in a 3:2 blue to yellow ratio. And this is straightforward. This is the type of thing we've seen over and over again. We can make some kind of ratio table, or you can just set up a proportion and cross multiply, however you want to do it. I'm just going to make a quick table. So if we have blue and yellow, I know that if I have 3 gallons of blue paint, I should have 2 gallons of yellow. And so if I want to know how many gallons of blue paint I should add, or rather, sorry, how many gallons of yellow paint I should add to 12 gallons of blue paint, well, how do I get to 12 from 3? Well, I can just multiply by 4, and then I get 12. And then I just do the same thing to the gallons of yellow paint, and I get 8. And of course, I can do this, multiply the quantities by the same number because they are in a particular ratio, 3:2. So I see that I need 8 gallons. And that's my answer. Okay, so this is a pretty simple proportional problem. So recall that the quantities of blue paint and the quantities of yellow paint are in a proportional relationship. So we could, for instance, graph them in a coordinate system, and we'd have the equation of a line. We could actually write down that equation. But I just want to write it explicitly that in this particular problem, there is and I'm going to use this word directly. I haven't really used this up till now, but I'm going to use it now to really differentiate it from when we look at an inversely proportional problem. But this is really a directly proportional relationship between, when you have a relationship, there needs to be two, people, or in this case, two quantities. So the quantities that are in a directly proportional relationship are the quantity of blue paint and the quantity of yellow paint. And that relationship is given by this ratio, 3:2. Okay, so it's a directly proportional relationship. So now let's look at an example that's actually an inversely proportional relationship, just so you can see the difference in the type of problem. All right, so here's another problem. And let's just read it. So 6 workers can paint a wall in 4 hours. And we'll make this assumption, otherwise this problem might be a little difficult to answer, but we'll assume that all workers work at exactly the same pace. Okay, so the question is, how long will it take 8 workers to paint the same wall? So 6 workers can paint a wall in 4 hours. How long will it take 8 workers to paint the same wall? So let's assume, that's a dangerous thing to do, but let's assume this is a directly proportional relationship. So meaning like the quantity of blue and yellow paint that are in a particular ratio. So I'm kind of assuming that there's a 6:4 ratio between workers and hours, and then I'm just trying to figure out, okay, how do I get from 8 to 6, and then that should give me the number of hours, right? I mean, that makes sense. So let's make a ratio table, or you can set up a proportion and cross multiply, however you like to solve ratios, or proportions, I mean. So we have workers, and we have hours. So we know that 6 workers is to 4 hours, so we kind of have our analogy, 6 is to 4. And then we would like to get to 8, right? So however you like to think about it, I'm just going to kind of think through it this way. So let me figure out kind of what 1 worker is. So 6 is to 4. Let me figure out what 1 is. So if we go and divide by 6, over here, let's divide by 6. So this is 4 over 6. Okay, and then let's see. I need 8 workers, so let me multiply by 8, and that'll give me 8 workers. And then if I multiply 4 over 6 times 8, well, that's 32 over 6. Okay, so what is that? Well, this is about 5 hours. Okay. Well, let's see. So it's going to be 16 over 3, so that's 5 1/3. So it looks like 5 hours and 20 minutes. Okay. So, I don't know, what do you think? Does that make sense? So just step back and we just set up the proportion. 6 is to 4 is 8 is to blank. Okay, 8 is to 5 1/3, which is 5 hours and 20 minutes. And we're done. Okay, so hopefully you notice that there's a big problem with this answer. So just step back and logically think about this problem. If 6 workers can paint a wall in 4 hours, if I add 2 more workers, does it make sense that it's going to take an additional hour and 20 minutes? So it's going to take longer for 8 workers to paint the same wall than it did 6 workers. Now, if they're distracting each other, maybe, but we're assuming that all workers work at the same pace. So this answer is actually ridiculous. There's something wrong with this answer. Okay, so no. We assumed this was a directly proportional relationship between the workers and the hours it takes to paint the wall, but that's not correct. And the reason it's not correct is because this is not an example of a directly proportional relationship. This is an example of an inversely proportional relationship. So now let's actually just try to solve the problem without thinking about what type of problem it is, just reason through it logically. And then we'll think about, okay, well, what is this saying? What is this new type of problem that we found? And what does it have to do with, say, multiplication, division, ratios, everything we've been talking about? So let's think about it. Okay, so we're going to take another stab at solving this problem. And we're not going to assume anything. And here's what I'm going to do. I'm going to do our favorite thing. I'm going to draw a picture. So here's my wall that I'm trying to paint. Okay, and this is the way I'm going to think about it. And this actually makes a lot of sense. Okay, I'm going to partition this wall into 6 equal parts. Okay, so here's, let's see if I can do this. So we'll do 3 panels that way and then 2. Okay, so here's 1, 2, 3, 4, 5, 6. Now what I'm going to say is that this will be worker 1's area of wall. This will be worker 2. This will be worker 3. This will be worker 4. This will be worker 5. And this will be worker 6. Okay, and now what do I know? Well, I know that each worker is going to work for 4 hours on their section of the wall. Not 41 hours, let's see. 4 hours, 4 hours, 4 hours. Okay, so now all these workers, I guess we're assuming, are working simultaneously, so it's a little confusing. But you can also imagine that if worker 1 worked for 4 hours, and then worker 2 worked for 4 hours, and then worker 3 worked for 4 hours, and so on, you kind of see that there's 24 hours worth of work to paint this wall. And that's really the way we want to think about inversely proportional problems, is that there's actually sort of a fixed product. So if we take the 6 workers and then multiply by 4 hours per worker, we get a total of 24 worker hours, as we'll call them. So over here we have 6 workers, 4 hours per worker, for a total of 24 worker hours. And we want to assume our multiplication definition here. So this is really number of workers. So I'm thinking about each worker as being an equal group, or maybe more specifically, I'm thinking about, each part of the wall that each worker is working on is an equal group. And then each one of those parts of the wall will take 4 hours per each worker, so 4 kind of units per one equal group. And then the total is what we're going to call 24 worker hours. Okay, so I'm sort of fudging together a new unit, this worker hours, but I'm just making it fit into this multiplication definition. Okay, so this is very naturally a multiplication problem. We have 6 workers, 4 hours per worker, so the wall takes 24 worker hours. Okay, so the way I like to think about that is if one person were to paint the wall, it would take that one person 24 hours, because this is telling me altogether there are 24 worker hours. Okay, and so hopefully that picture is starting to make sense. Now, let me go over here and draw exactly the same wall. Now, it's not going to be exactly the same size, but just use your imagination, okay? And now let me partition this into 8 equal parts. So let's see, I need to draw 3 lines this way. Now, let me be consistent with colors. So we'll partition this wall into 8 equal parts, because we're going to have 1, 2, 3, 4, 5, 6, 7, 8 workers. But we know from what we were given that it's going to take 24 worker hours. So this is actually just a division problem now, because I know that altogether this is going to take 24 of these worker hours. But I'm just evenly dividing them amongst 8 workers, or 8 equal groups. So I know I have 8 workers. And what do I not know? I have an unknown number of units in one equal group, or in other words, an unknown number of hours that each person is going to work. So this will be hours per worker. And of course, if all the workers work simultaneously, then this will actually just be the total amount of time it takes to paint the wall. And so now it's really easy to see the answer. It should be 3, right? So hopefully with a little thought, you can recall that 8 times 3 is 24. So if I just divide the 24 hours amongst all of these panels, because each panel has its own worker, 3 hours, 3 hours, 3 hours, and 3 hours. There we go. So we see that it's going to take 3 hours to paint the wall. And that makes a lot more sense, right? Because if I add 2 more workers, one way I can think about it is I'm adding 33.33% more workers, so I should get a reduction in time by kind of a similar factor, right? So, another way I can think about it is, I'm adding 2 more equal groups, and so I'm just sort of having to repartition these equal groups into equally sized equal groups over here. I mean, you can think about it as much as you want. I mean, maybe the easiest way to think about it is just that there's this fixed product, right? So the 24 is what's being fixed. Now the difference between, say, like a directly proportional relationship is that either the multiplier or the multiplicand was being fixed, and then the multiplier could vary directly with the product. But here, actually, the multiplier and the multiplicand are varying inversely. So let's talk a little bit more about this, but hopefully this example makes sense and gives you kind of an idea of what you need to look out for inversely proportional problems. Okay, so I want to give an overview of directly proportional relationships and then inversely proportional relationships, now that we've seen an example of each. So here's the idea with directly proportional relationships. I mean, this is going to be review because we've spent a lot of time talking about directly proportional relationships. It all starts with a ratio. So we have quantity 1, and we have quantity 2, and then we have a ratio. So the ratio of quantity 1 to quantity 2 is something like A to B. And from this ratio, we get an equation. So let's introduce some variables. So let's say x is the amount of quantity 1, and then y is the amount of quantity 2, then what we do is, however you want to think about it, you can sort of go through 1 with quantity 1. So we're going to end up with something like y, the amount of quantity 2, from some amount of quantity 1. Well, what we're going to do is we're going to multiply by b over a, this quantity x. Okay, so this is the equation for this directly proportional relationship. And so y and x are said to vary directly. That's one way to say it. So this number b over a, it's the value of this ratio, but it can also be thought of as a constant of proportionality or constant of direct proportionality. And so from this we get a graph. And we know what this graph looks like. It's the equation of a line passing through the origin, where if this is x and this is y, then here's, say, a, and here's b. And we know we, of course, pass through the point AB. And then if I can draw a straight line, this is what the relationship looks like graphically. Okay, so, when I increase x by a, I'm going to increase y by b. Okay, so I think that's all well and good. Another key thing about directly proportional relationships, particularly when you're trying to recognize directly proportional relationships, is something like, so if x increases, y increases. And notice this was how we sort of were able to tell that the previous example wasn't a directly proportional relationship, because as the number of workers increased, the amount of time it took to paint the wall decreased. Okay, so if we have a situation where we do have a directly proportional relationship, as one quantity increases, the second quantity is also going to increase, and those quantities are going to increase together proportionally by this factor b over a. Okay, so that's just a quick review of what a directly proportional relationship looks like. Okay, so let's look at what an inversely proportional relationship looks like. So here we're not going to start with the ratio. But what we are going to start with, again, are two quantities. So we have quantity 1 and we have quantity 2. Okay, and so how do we sort of describe the relationship between quantity 1 and quantity 2? Well, here's how we do it. So let's again say that x is the variable amount of quantity 1. And then y is the amount of quantity 2. So the idea is that rather than thinking about, okay, as x increases, y increases proportionally, somehow the product of x and y is staying fixed. Okay, and the best example I can think of to sort of motivate this example is looking at rectangles with the same area. Okay, so let me just draw a couple pictures just to motivate this. You can have kind of a long, skinny rectangle where this is x and this is y. Okay, so then what is that going to give me? That's going to give me some area. But I can imagine another rectangle that maybe wasn't so long and skinny, where now this is x and this is y, where the area is actually the same. So just imagine two rectangles that have the same area but different dimensions, right? So the length and the width of this rectangle are different than the length and width of this rectangle. But what's the same? I get the same area. So when I multiply x and y together, I'm getting the same thing. And so you can see how if x is going to be decreasing, then y better get longer to sort of account for that decrease in x. Whereas if x is longer, then y is actually going to be smaller. So the idea is that you have x times y is equal to a constant. Okay, and this is just a fixed number. So in our example with the workers and the hours to paint the wall, it was 24. It was like 24 worker hours. That's how much it's going to take, how long it's going to take to paint the wall. And then the number of workers, the equal groups, and the units in one equal group can vary together, but they're varying inversely. So one increases, the other has to decrease, and vice versa. So again, sort of the takeaway fact is that x increases, y is going to decrease. But not just decrease in an arbitrary way. I mean, it really decreases by the same factor. Now, if we look at the graph of an inversely proportional relationship, what are we going to get? We're not going to get the equation of a line anymore. We're actually going to get a what's called a hyperbola. So if here is maybe, let's see, so we want x times y to be c. So let's say that, okay, so here's x and here's y. So if we plot a couple points, well, let's say this is 1, okay, then what is x going to be? Well, it's going to be equal to c. Okay, so here's this point right here. Let me actually draw it right here, so c. So if y is 1, x is c, and then if x is 1, y should be c. Okay. Then we sort of have everything in between. So the graph is going to look like this. It sort of hugs the y-axis and hugs the x-axis like that. And so the shape is called a hyperbola, if you remember. Maybe that's not so important to know, but I mean that's the graph in the coordinate plane of an inversely proportional relationship. Okay, so that's probably more than you wanted to know, but that gives you the two perspectives between inversely proportional and directly proportional. Directly proportional, the multiplier and the product are varying together directly, or the multiplicand and the product are varying directly, but in an inverse proportional relationship, the multiplier and the multiplicand are varying together. One goes up, the other goes down, and vice versa.